So good morning everybody. In today's lecture, we will discuss another planning technique, that is plan space planning. Yesterday we have seen a goal stack planning technique, and in goal stack planning technique, we saw that we put the sub goals, that means the final goal containing sub goals on the stack along with the operators. And as and when those sub goals are satisfied, we remove those goals from the stack, and algorithm terminates when stack is empty. We saw in goal stack planning that it's a linear planning technique where the order in which the goals or actions has to be performed, or operators corresponding to actions that you are going to perform, that is linear in nature. So one by one those goals has to be satisfied in totally order fashion. So in orderly fashion, we have to perform set of actions. Most of the time it is not possible for us to decide, to take decision in advance about the order in which actions will be carried out. So sometimes there is a possibility that when you are trying to satisfy two sub goals to achieve a goal G, for example, suppose there is a goal G that we have to achieve. To achieve this goal G, there are two sub goals, G1 and G2. Both has to be satisfied. There might be a case when you try to satisfy G1, then this G2 becomes false. If you try to satisfy G2, then G1 becomes false. So G1 cannot be satisfied when you try to satisfy G2, or while satisfying G1, G2 becomes false. So that situation is called as Sussman's anomaly. And in your book, one specific situation has been given corresponding to block wall problem. You go through that, which has resulted in Sussman's anomaly. In addition to that, it's not very efficient goal stack planning, since it's a linear planning technique. So these problems are resolved in plan space planning technique, which we are going to discuss today. So in today's lecture, we will be discussing how this plan space planning work, followed by one example we will solve on plan space planning. So there will be no break in today's lecture, and in last lecture, most probably next week, uh, we will discuss remaining part of this unit, that is graph plan and constraint, what is constraint propagation. So our next lecture will be most probably last lecture for our course, artificial intelligence. Before continuing what plan space planning, if you have any doubt related with goal stack planning, which we have discussed yesterday, we can discuss it right now. Otherwise, we will start plan space planning. If you have any doubt, you can ask corresponding to goal stack planning. Any doubt?
No, sir.
No, sir. Okay. For this planning part, you will have to refer Rich and Knight's book. Along with that, you can refer the material available on the net, specifically on NPTEL, Khemani's Professor Khemani's lectures are there freely available. So you can refer them, or otherwise I will put these lectures on YouTube channel. So we'll proceed further. Before going to plan space planning, let us first try to understand what is state space planning, which we have discussed yesterday. In state space planning, we know that the program searches through space of world states, or a program searches through the states, and that forms a state space, seeking to find path or paths that will take from initial state to the goal state. So we start with initial state and then we move through the intermediate states till the goal state. Okay, so here circle denotes state and line between two circles that denote the transition from one state to the another state. So a program which will search through this state space or space of world states to find out a path from starting state to the goal state, that is what state space planning is. So we have discussed such a techniques earlier in our course. This state space planning is not flexible because the plans generated in state space planning are totally ordered, and it assembles these plans exactly in the same order. So for example, if this is a solution path from starting state S to goal state G, for example, solution path is S, B, D and G. S, B, D and G. So here this is a total order. First you will start with state S, then move to state B, then D and finally G. So this is called as totally ordering of states. So therefore it is not flexible. Therefore we have plan space planning. This plan space planning is also referred as partial order planning. In mathematical foundations, we have discussed what is total order, what is partial order. So same concept has been used out here. So this partial order planning is also called as POP. Now in partial order planning, the planner, that is plan space planner, search through space of partial plans. Unlike in state space planning, we have seen that it searches through the space of world states. Okay. Here, instead of that, planner will search through the space of partial plans. Now, what are partial plans? Which are set of actions that may not be totally ordered. That means that may not be in a specific rigid sequence. And here, planners are plan based and introduce ordering constraints. How those steps should be ordered. So for that purpose, we have ordering constraints as necessary whenever required in order to avoid unnecessary searching through the space of possible ordering. Okay, so in short, in partial order planning, planners introduce constraints whenever required. So unless and until they are required, those constraints are not introduced. So that will save a lot of efforts. So this is called as principle of least commitment. And in our real life also, we most of the time use this principle of least commitment. That is, it's the idea of never making a choice unless required to do so. In other words, only do something when it is necessary. Otherwise, don't plan things in specific order. The advantage of using this principle is that we try to avoid doing work that might have to be undone later. Hence, that will avoid a lot of uh, wastage of your time, wastage of the time or work. So unless and until it is very much necessary, don't do certain things. This is called as principle of least commitment. Now in planning we are going to use this. In the planning, one application of this principle is to never order plan or steps in your plan unless they are required for some reason. And you will find out, therefore, planner exhibit this property because ordering of this constraint will only be inserted when they are compulsory or necessary. For example, now whenever I go to my home from office, if I order my steps, if it is a totally order plan, how I will reach to my home? I will start from the university uh, school, our school of computer sciences, and reach to Bamburi. From Bamburi, Shiv Colony. From Shiv Colony to my place, home. Now this is a totally order plan. So in this way, I will reach to my home if plan is rigid plan. But most of the time I don't follow this particular plan or technique. Sometimes what I do, I see that there is no rush near Madraj Park at Navjivan shop. So I remember something that I will have to carry. I go to the Navjivan shop, buy something which I may require in the next week or day after tomorrow. Along with this, when I reach to Shiv Colony, I remember that tomorrow morning I will have to get milk, but tomorrow morning I have lecture early in the morning. So to save that time, I see that there is a milk shop around. I carry milk with me and then reach to home. So this is something like list commitment principle. I have followed here list commitment principle. I am not committed to the certain set of steps. I change the things depending upon the situation. So always it is not necessary that now suppose while going I see that there is a rush at milk shop, then I will not visit milk shop. It's better to get the milk tomorrow morning. Same thing is available at Madraj Park. If it is crowded, Navjivan shop is crowded, I will not visit that shop. I will directly come to home. So in our real life, you will find out you might be also following such a list commitment principle, and that works, that saves lot of your efforts. For example, while coming from hostel to the school of computer sciences, sometimes while coming you see that there is nobody at ATM near the administration building. So you go to ATM, withdraw money and come to the department. Although your goal was to reach to the department, but in between that you use this list commitment strategy. You saw there was nobody at ATM, so you finished that work because tomorrow or day after tomorrow, there might be a case that you need to withdraw money. So you realize that you can save a lot of time and efforts if you do that right now. So you visited ATM and then came to the department. So this is list commitment strategy which is used in plan space planning. Okay. On the other hand, situation space progression planners, that means totally order planner, make commitments about order of steps as they try to find out solution, therefore make mistakes from poor guesses about the right order of steps. Okay. Now let us see how it works. In plan space planning, we call that as non-linear planning. Reason is we can modify any part of the plan. Therefore, it is not linear. These approaches do not constrain to focus on any one of sub-goal continuously. So you may change your focus in between if required. You can shift attention midway. Therefore, can solve problems like Sussman anomaly. Because Sussman anomaly that results in because of that totally ordered steps. And if you remove that constraint, then you can resolve that particular problem. So in plan space planning, program searches through space of plans, seeking a plan that will take it from initial state to the goal state. Algorithms represent plan as set of actions arranged in partial order. Hence also referred as partial order planning. Here we have set of actions which are arranged in partial order. In goal stack planning, set of actions were arranged in totally ordered sequence. So that is the difference. So by searching through plan space of partial order plans, that is each node in plan space represent a partial order plan and each arc in plan space will represent transformation from one plan to another plan. We will see how it is. For example, by adding a new step or adding a temporal constraints between existing steps. So that's how that makes it flexible. Let us try to understand this with a simple example. Which will explain what is a partial order plan. Example is getting ready in the morning and goal is you have to put your socks and shoes on. Okay. So uh, there is a starting state and finish state. At the end, when goal is satisfied, left shoe on will be true and right shoe on will be true. So left shoe on and right shoe on when that goal is satisfied. What is the goal? Getting ready in the morning. Part of that we are considering. So this can be done by performing several sub steps like uh, first you wear left sock, then left shoe, okay, or you wear right sock, then right shoe. If you wear left sock followed by left shoe, then left shoe on will be true. If you wear right sock followed by right shoe, this sequence is important. This has to be performed first and then you can wear shoe, right shoe. So if you perform right socks, wear right socks first and then right shoe, then right shoe on will be true. Understood the example? This can be done in now different ways. Your objective is getting ready. For that purpose, one part we are considering that you will have to wear shoes. To wear shoes, you will have to wear socks. Now, again, there are two sub steps, two sub goals. To wear left shoe, you will have to wear left sock. To wear right shoe, you will have to wear right sock. Okay. Any question up to this?
No, sir. No, sir.
Okay. Now this uh, plan will result in several subplans. Like now this can be done in different ways. One, you first wear right sock, then left sock, then wear right shoe and left shoe. So at the end, left shoe on and right shoe on will be true. This is plan 1. Okay. Same thing can be done in another way. You first wear left sock, then right sock, then right shoe, then left shoe. So what change we have made here? Instead of wearing right socks first, we wore left sock, then right sock. Earlier case, right sock and left sock. These two steps are in the same sequence. So still you will be able to achieve the goal, that is right shoe on and left shoe on will be true. This is second way. Same thing can be achieved. Same goal can be achieved in third way also. You wear right sock, left sock, same sequence as that we have followed in plan 1. But here we have changed sequence of wearing shoes. Now first wear left shoe and then right shoe. No problem, that can be done. Still here you will get left shoe on true and right shoe on true. So this is third possibility. Fourth possibility is another way, same thing can be done. You wear left sock and right sock after that. That is as that of plan 2. But after that you change this latter sequence. You wear left shoe first and then right shoe. Instead of right shoe here, you wear left shoe and then right shoe. So at the end, again, no problem here. Right shoe on, left shoe on will be true. Fifth possibility, you first wear left socks. Socks has to be wear first. Left socks, then left shoe, right sock, and then right shoe. Still no problem. Here left shoe on and right shoe on will be true at the end. And last, sixth possibility, instead of left, you wear right sock first, then right shoe, then left sock, then left shoe. Still, same goal can be achieved here. So these are that will result in this plan will result in 6 totally ordered plans. Now this arrangement is totally ordered. You have to follow this specific sequence in this order only. So arrow is showing the order from start to the finish. So these are called as totally ordered plans. Now if I do wear right shoe, for example start another totally order plan, then right shoe, is it a valid sequence? Then right sock, is it valid?
No.
No. Why? What is the reason?
Because we were first sock.
Right, because always we have to wear socks first and then shoe. Okay, so we cannot wear sock and shoes. That is first wear shoe and then sock. That cannot be done. So it's not valid. So only valid 6 totally ordered plan will be the result of that particular plan. Okay. Now let us come to what is a partially ordered plan. So in previous example we have seen this is a totally ordered plan. In plan space planning we are interested in partial order plan. Now this POP or partial order plan we will represent with a graph. Okay, and this graph will describe temporal constraints between plan steps. These are the steps, for example S1, S2, S3, S4 and S5 here. These circles they show the steps. Each node will represent a single step in the plan. Okay, that is instance of one of the operator. An arc will designate temporal constraint between two steps. For example, this arc connecting S1 and S2 that defines a temporal constraint. Now, this uh, graph containing 5 steps, okay, S1, S2 up to S5 represents a temporal constraint. S1 uh, is less than S2. For example, what is meaning of this? That S2 follows S1. That means first S1 should occur and then S2. That is a temporal constraint. So time dependence is there. First S1, then S2. So therefore we say S1 is less than S2. In partial order in mathematical foundation, same concept we have studied. Lattice in lattice. Okay. Similarly, S1 is less than S3 because S1 comes first and then S3 because of this arrow direction. Now S1 is less than S4 also. S1 is less than S5. Similarly, S4 is less than S5. Right? All these are temporal constraints. So this partial order plan represents following 3 totally order plans. This example that is showing 3 temporally uh, partial order plans, total order plans. This is a partial order plan. So that is representing 3 total order plans. What are those? First is this S1 followed by S2. Okay. Then S3, S4 and S5. Or S1, S3, S2, S5. Or you can go to S4 and then S5. Or S1, S3, S4, S2, S5. Only you will have to keep in mind that you should follow this temporal constraints. In lattice, we have represented this as this S1 is less than S4. That means S1 comes first, then S4 comes. So this is ordering relation. Okay. Now, what are components of a partially ordered plan? We will have set of actions as that of uh, goal stack planning we saw. We have operators. Along with this, now here we will have ordering constraints. For example, ordering constraint out here shown is A is less than B. What is meaning of this? How to read this? That A is before B. This represents A is before B. Okay. So this represents the ordering relation. So here you should be careful about the cycles. Like if A comes before B and B comes before A, then that will result in a cycle. Again understand, A comes before B. For example, somewhere we have A and somewhere we have B out here. So A comes before B, and similarly if we have constraint that B comes before A. So that will be something like this. B comes before A. So that will result in a cycle. So avoid such a cycles. Okay. Third component, we will have set of causal links between actions. Something like this. For example, suppose we have A, action A and action B. So there is a transformation from action A to action B, state A to state B, and there is a predicate P, for example, that must remain true when there is a transformation from A to B. So we read this causal link something like this, that A achieves P because P becomes true. A achieves P for B, and this P should remain true through the time interval from A to B. Now what is this? Let us understand this with a previous example. Consider a state right sock. Then we perform action right shoe. Right sock and right shoe. Let us go back. Right sock and right shoe. These two. Okay. This first and then right shoe next. This part of this total order plan we are discussing out here. Right sock and right shoe. Transformation from right sock to right shoe. Now during this transformation, right sock on has to be true. Suppose this is a predicate, right sock on must be true. So in between this, some other action should not make this right sock on false. So make sure that in between right sock and right shoe, this right sock on will be true all the time. So this type of link is called as causal link in partial order plan. Okay. Now fourth component, we have a set of open preconditions. So we reduce that to empty set without introducing contradiction. So we will see example, then you will understand it in better way. We start with the initial plan. Now what this initial plan is? Initial plan describes unsolved problem consisting of two steps initially. One is start and another one is finish. Any plan initially will at least contain these two steps, start and finish. Of course, start has to come before finish. This relation should hold there. Now, both start and finish have null actions associated with them. At start and finish, we do not perform any action. So there is no operator associated with start and finish. Similarly, this way, that example we have seen, we start with a start step and then finish at the end. Start to finish. Start has no and effect is to add all the preconditions that are to start does not associate with action that is associated with action. Condition is required to start this step. Every action, as we have seen, later we action has preconditions that is has to be factor. That means as a result of that action, concept we have seen in goal stack planning also. So start step has no preconditions and its effect is output will be is to add all the preconditions that are true in the initial state. So some initial state will be given to you. So all those initial conditions or predicates which are true initially, so that will be in the effector of this start state. Same way, finish state is your goal state. So it will have precondition but no effect. Okay. So this finish state will have preconditions associated with it. So because of that, you will get the goal that has to be achieved, which will become true, and it will not have any effect. Okay, as opposed to the start state. Start state will have effect and no preconditions. Finish state will have a goal state, that is it will have a goal state as its preconditions, but it will not have effect because that is the final state. Okay, the goal is achieved. So by defining problem in this particular way, planner will start with initial plan and manipulate it until they come up with a plan that is a solution. This is how this plan space planning in general works. Okay. Now, what is a solution? Now, solution is a plan. What is a solution? Solution is a plan that an agent can execute that guarantees achievement of the goal. Okay. The solution at the end is a plan that agent can execute that guarantees achievement of the goal. So what we do, we accept this partially ordered plan as a solution because solution is complete and consistent plan. So these two concepts are important. What is a complete plan and what is a consistent plan? A complete plan is a plan where every precondition of every step is achieved. Because to perform any step, first you should satisfy its precondition. Then you will get a result. So in complete plan, every precondition of every step will be achieved. Okay. And in consistent plan, there are no cycles and no conflicts with the causal links. Okay. So complete plan, in complete plan, every steps preconditions will be satisfied. In consistent plan, there are no cycles and no conflicts with the causal links. We will understand what is meaning of conflicts in the causal link when we will discuss that example. So consistent plan with no open precondition is a solution. So what is a solution therefore? A solution is a consistent plan with no open precondition, that means all preconditions are satisfied, and which is consistent, that means there are no cycles. So that is called as solution. Now how to create partially ordered plan? There are two main flaws or reasons why a given plan may not be a solution. So always we should be careful about resolving the flaws. Okay. What are those two flaws or reasons? One is unsatisfied goal or open goal we say, and another one is threat. What is open goal or unsatisfied goal? Obvious. That is, there is a goal or sub goal that is not satisfied by the current plan state. So if it is not satisfied, that is not true. The corresponding predicates are not true. So such a goals are called as open goals. So we don't want such unsatisfied goals. All sub goals should be satisfied. Second one, threat. This threat has to be removed. What is a threat? It is caused by a plan step that could cause undoing of needed goal if that step is done at a wrong time. Again, I am repeating. Threat is what? Threat is caused by a plan step that will cause undoing of needed goal if that step is done at wrong time. For example, there is a state S1, another state S2. Effect of this S1 is some predicate P, that means P has to be true, which is a precondition for S2. Again, I am repeating. We have state S1 which comes before S2. After execution of S1, its effect is, result is predicate P which is true, which is a precondition for S2. That means to execute S2, P has to be true if this is the case. And suppose there is another state S3 whose effect is not P, that occurs between S1 and S2. Okay, S3 has occurred between S1 and S2, and because of that this P has become not P. But precondition of S2 is P. So this is called as threat. Okay, S3 has been introduced at wrong time. Okay, and that is undoing the needed goal which is required, needed precondition which is required, that is P which was true, that is false, so S2 cannot be executed. So we will define the plan modification operators that detect and fix these problems. So we have solution for these problems, that means to resolve the unsatisfied goals and to remove the threats. What are those plan modification operators? So two plan modification operations we are going to perform. One is simple establishment and another one is step addition. This is an important concept in this plan space planning. Now what is establishment? Establishment is solve the open precondition, that is unsolved goal. That is, if precondition P of step S does not have a causal link to it, then it is not yet solved. This is called a open precondition. Suppose there is a step S. Now precondition of step S is suppose P. Okay. So P should be true to execute this step S. If this is the case, it does not have a causal link to it. So if we do not have a link to this, so this is called an open precondition. So there should be a link which will make this P true. So there are two ways to do this. One is simple establishment. So this is find step T prior to S. So for example, out here we will find out step T prior to this S, in which P is necessarily true. That means this T will make this P true. So effect of this T will be P. Effect of this T is P. Effect means result of this T is P. Then you can add a causal link from T to S, because effect of T is P, which is a precondition for S. So this is called as causal link. So this is called as simple establishment. Now, what is step addition? Add a new step T. So this step we have added that contains its effect list P. Effect list will contain P. Then add causal link from T to S. So we have added this step. This is called as step addition, and this is establishment. We have established a link from T to S. So add a step so that its effect will be, or its effect will satisfy the precondition of the following state. So that is step addition, and because of that, that will establish a link from that added state to the state in question, that is S. So this is adding a link, that is simple establishment. So these are plan modification operations, simple establishment and step addition. Any question up to this? Because this is an important concept which you will be using while developing a partial order plan. Understood up to this?
Yes, sir.
Yes, sir. Okay, so move further. Now, how to remove a threat? Threat removal, that is called as declubbering. Before that, let us understand what is a threat. We will repeat again. Threat is a relationship between step S3 and a causal link S1 and S2. For same example, suppose we have step S1 and step S2. There is a causal link from S1 to S2 and precondition of this S2 is P. Okay. So to perform S2, P has to be true. Then there is the step S3 whose effect is not P. There is a step S3. If you execute it, uh, output will be not P. And if the temporal link occurs between S1 and S2, suppose S2 occurs in between this S1 and S2. So this will look like this in that case, S1, then S3 and then S2. So effect of S1 is P, effect of S3, that means result of executing S3 is not P. Okay, and but the requirement of this S2 is P, but it is getting not P. This situation. Okay, if this is occurred, we say that S3 would clobber, this S3 would clobber the goal P produced by S1 before it can be consumed by S2. Right? Again I am repeating. S3 is clobbering the goal P which is produced by S1. Okay. Before it is consumed, because that is requirement for S2, before it is consumed by S2. So what to do? If this is the case, what to do? Now there are two solutions for this. Fix this by ensuring that S3 should not occur between S1 and S2. Make sure that this S3 should not occur between these two, S1 and S2. This is called as protection interval. This can be done by using promotion or demotion. Now what is promotion? Promotion is force the threatening step to come after the causal link. So what we will do, we have, okay, we will remove this. So we have S1, we have S2, precondition is P here. So what we will do, if S3 is clobbering, we will, suppose if we perform promotion, so we will, what we will do, force the threatening step to come after the causal link. So we will add S3 after S2. That is S3, S2 should come before S3. So this is called as promotion. We are promoting this protection interval. Okay, so this protection interval will occur before this S3. So after that, if this S3 makes this P false, no problem for us. So this is called as promotion. So now we will not have any problem. S1 and S2 will occur without any problem. Another solution is you perform demotion. In demotion, this is promotion. This is promotion. Now what we will do, we have S1, we have S2 whose precondition is P. In demotion, we will force the step S3 to come before the causal link. So S3 will come before the causal link. Okay. So we will write that like this, S3 should come before S1. So because of this, now the effect of S3 is not P, but S1 will make this not P again. So no problem, we will not have any problem between S1 and S2. So this is called as demotion. What you have demoted? You have demoted this protection interval. So S3 will occur first, threatening that step will occur first, and then our protection interval. So we have demoted the protection interval, so therefore we call this as demotion. Okay. So this one of this can be introduced to remove the threat. Understood? Any question? So if there is no question, we will move further. So in general now, it's a non-deterministic algorithm. TOP is a non-deterministic algorithm where the choices are made. Various search methods you can use for implementation of this, like breadth first search, depth first, or iterative deepening DFS to explore the space of possible choices. We will maintain, what we will do, we will maintain agenda of goals that need to be supported by links, where agenda element will be a pair QA, ordered pair, where Q is a precondition and A or AI needs supporting. So Q is a precondition of AI. Right? What we do, we initialize a plan with a null plan, that is start and finish, and agenda to the conjunction of goals, that is preconditions of finish. That is how your plan will start. So goal, we know we have given the starting state. So conjunction of goals, that is the precondition of finish which has to be satisfied. So that's how your plan will start. Algorithm will terminate when all preconditions of every action in the plan are supported by causal links which are not threatened. Right? Simple algorithm. Now let us consider execution of this plan space plan with a example. That example is a robot agent example, and in this example the robot needs to solve the following. The goal is get a bag of milk, bread and a good book. So we will discuss, we will now prepare a complete plan space plan for solving this particular goal. Before that, let me ask you, have you understood in general the process? Any question up to this? Because now whatever we have discussed, we are going to use for solving this problem. So if you have understood, now tell me the first step. Simple one, simplest one. Any question on the procedure to develop a plan? If no question, now tell me the first step. How to start with? Simple it is. First step is the simplest one of all. Already I have told you it. We'll start with this start, finish, right? Two states, start state and finish state will have, and also I told you finish state has goal state as its precondition. Start state will not have any precondition, it will have effect. So your start state is given to you. Finish state, that means goal state, is also given to you. Now come to problem, getting a bag of milk, bread and good book. Now knowledge representation that we have discussed in last uh, discussion, last unit, that we have discussed mathematical logic, that we are going to use for representing a knowledge. So all these are the predicates. Start state is given, that is means robot is at home. At home means robot is at home. Store sells milk. Store sells bread is true. B store, that means bookstore. B store sells book. Okay. So this is given initially. What we have to achieve, that uh, robot will have milk, robot will have bread, robot will have book, and robot will be at home. So that is the goal that we will have to achieve. So as I told you, initially you are going to start with start state, and you will have to achieve final state, which is given. Start and final. Start state does not have any precondition, but it has effect. What is that? It is given. That is at home is true. Then sales store milk is true, and you can say sales predicate store comma milk is true, and store sells bread is true, and B store sells book is true. Right? This is given. So this is the effect of execution of start, which is the initial state. This is given. What at the end you will have to achieve? So final state has no effect. It has preconditions, which are goals that has to be achieved. So at the end we want have milk should be true, and have bread should be true, and have book should be true, and robot should be at home. This is the first step. Understood now? Initial state, start state, final state. Start state has effect, which is given. So it will start with this. Finish state has precondition, which is a goal that will be true. So you will have to convert initial state into the final state. Now understood?
Yes, sir.
So same thing now I have drawn out here. This is how initially your plan will look like. Same thing. This is given at home. Robot is at home. Store sells milk. Store sells bread. Store B store bookstore sells book. At the end we want robot will have milk. Robot will have bread, book, and robot will be at home. Now in between that we will have to add steps so that we can convert this initial state into the final state as usual process. Now for this purpose we must know what are the operators available, what actions that you can perform. So two actions are given to you. One is buy and another one is go. Okay. So to have milk, what is required? Robot should buy milk. So buy action is required. So that is given to you. So this buy X is given. Okay. Buy X, precondition is robot is at store. It should be at store and store should sell that X. Okay. So buy X is given to you. This is given. X is a variable. Precondition is now to buy X, for example, to buy milk, you should be there. Okay. So therefore, precondition is you should be at store. Robot should be at store. This is one of the precondition. And another precondition, store should sell that X. So store sells that X. These two are required to perform this action. So robot should be at store. Suppose X is milk. So to buy a milk, robot should be at store and store should sell milk. If I replace X with milk, what will be the effect of this execution of this effect? Yes, now tell me this. If you perform buy X, what will be its result? Logical. Yes, repeat.
Have X.
Right, have X, correct. Have X. So if I replace X with milk, to buy a milk, robot will be at store and store will should sell milk. If both are true, then robot will have milk. Right? Correct. Now this is one action that is available with us, and second action available with us is go. Because how you will go, the robot will move from one place to the other place. Okay. So go there, suppose. Go there. What is precondition and what is effect? Go there. This is the action. To perform this step, precondition is robot should be at here. Okay. And effect will be robot will be at there. Initially it is at here, then it will be at there, and at here will be false. Okay. So precondition is, yes, go there. Precondition is at here. Instead of that, sir, this is just for understanding. Precondition is at here. Robot is at here. Effect will be at there. If you perform go there, so robot will be at place there. Yes, and at here will be
Negation.
false. Negation. At here will be false. Instead of there and here, you can have variable name x and y also. Like go y. Precondition is to perform this. Precondition is a robot should be at x, and effect is uh, at y. Robot will be at y and not at X will be false. Because we know that if robot is at Y, that means robot is not at X. But system will not understand, so therefore added that predicate, not at X. Okay, so two actions are available with us to perform this transformation, buy X and go Y. So now let us understand this. Uh, what we have to do, we want this have milk should be true. Okay, so to make this have milk true, you will have to add a step. Okay, effect of this buy X is have X, right? So to get this, that means we have to add this step. Same thing we have done in goal stack planning also. You check the result. So here if you want have milk, you should buy milk. Am I right? To make this true, we should execute this step buy milk. Yes or no?
Yes, sir.
So what we will do, therefore we will add a step addition we will perform, we'll add out here. Okay, so that I have done out here, buy milk. This step has been added here so that have milk will become true. Okay, so buy milk, its effect is have milk. Precondition has to be satisfied. Robot will be at store because milk store sells milk. So robot is at store and store sells milk. This has to be true. So is it true? Yes. Robot is at
No.
no. Okay. Uh, robot is not at store. Robot is at home, right? But store sells milk is true. This one is true. So one of the precondition is satisfied, but other one is not satisfied. Okay. To make this have milk true, buy milk has to be executed. To execute buy milk, precondition is at store and store sells milk. So store sells milk is true initially, but at store is not true. At home is true. Understood up to this?
Yes, sir.
So now what we have to do? We have to anyway make this at store true. So that we will do afterwards. Now let us come to this have bread. Same way we will add here buy bread. So we will add this step buy bread. So that will make this have bread true. Okay. Similarly, you want have book true. So to have book, you should buy a book. So buy book has to be added. Right? Got up to this?
Yes, sir.
We are trying to prove the goal now, satisfy the goals. And we are going to prepare a plan space plan, partial plan solution for that. Now, for buying bread, precondition is store should sell bread. Yes, that is true. Another precondition is robot should be at store, which is not true. Same way. Okay, so one is satisfied, another one is not. Here also, to have book, Robot should be at store, which is not true, but store should sell book. So yes, it is true. B store sells book. Okay. So uh, this will be true, but one is not true. So B store sells book is true, which is the precondition for buy book. So that type of action is available with us. So your plan will look like this now. Same thing now neatly drawn. This is the partial plan. Added step addition we have done: buy milk, buy bread, buy book. Okay. Up to this point, got the process.
Yes, sir.
Now what to do? What is the problem? Robot is at home, but we want it should be at store. So how to satisfy precondition of buy milk, which is at store? So you will have to find out action whose effect list will contain at store.
Go there.
Yes, right. So if you perform go store, then at store will be its effect. So you will have to add go store step addition you will have to perform. Okay. So in between this you are going to add this step. Okay. Like this. So from start, go to the store, then you will be at store. You means robot will be at store. Then at store will be true. Effect of this go store is at store and not at
At
home.
home.
Okay, not at home. So at store will be true, which is a precondition for buy milk. So therefore, you have added this go store here, right? In between this start and buy milk, so that preconditions of this buy milk will be satisfied. Same thing you can do out here also. Now for this also go store, sorry, at store is a precondition. So from this you remove this, from this you go to the buy bread. So now at store will be true here, right? So I have added this causal links from go store to buy milk and buy bread. Remove this, correct? So here also at store will be true. Store sales bread is already true. So this will give you the result have bread. Okay. Understood up to this?
Yes, sir.
Uh, this neatly is shown out here. Added this go store here. Step addition I have performed, right? Then that will add now these two links, additional links. Okay. S1 step has been added. Now similarly, to buy a book, you should be at bookstore. So at bookstore is not true. So you will have to add a step, go bookstore. So that step has been added out here. ठीक है?
Yes.
Now what is left? Anybody can make out. Is it over now?
Go to at home.
Right. One more. Now robot is at store. Huh? Out here also robot, what will be the result of buy bread? Result of execution of this? Have X, and because of that robot will be at store only, because robot is at store and robot has a bread. But goal required is that robot should be at home. Robot should carry all this to home. Uh, that is one thing. Any other task that is left over? See out here. Robot suppose as perform here you have performed started go store. So robot is at store, bought the milk. So robot will have milk. Then what?
Buy bread.
Same. Robot will buy bread. Same store is selling bread also. So robot will have milk as well as bread, no problem. But robot is a store. To perform now this go to big bookstore. Robot is at store, but robot has to buy book also. But robot is at store now. Or suppose this is performed first. Bookstore. So robot will be at bookstore. Okay. So robot has to buy bread and milk also. Suppose robot has bought milk and bread first. So robot has to go bookstore from store. Okay. So from this store, robot has to visit bookstore. So what we will do, the steps that I told you, because for this go bookstore to perform this, the precondition is at home. Robot should be at home. So what we have done, go back, how to do that? Promotion and demotion, right? So these steps you will have to incorporate. So what you will do, uh, demotion I will perform in this way. So one thing that I can do, from go store, you can go to this bookstore, okay, and then you robot will have book from this step to this step. Okay, so this can be done from S1, perform S3. What I will do, I will, in addition to that, perform demotion. This link have been added. Okay, I will do it out here. Since robot it at store, I will add a causal link from this S2 to S3. So demotion I will perform. Similarly, from this buy bread, I will add a causal link to this S3. So now robot will first buy milk and bread and then go to the bookstore. So this causal links have been added. Okay, in addition to this, from S1, uh, robot can go to S3. This is shown with blue arcs. So this is called a devotion. Okay, that we have discussed earlier. So now let us understand this. Robot it as home, it will go to the store, right? Buy milk and bread, then go to the bookstore, buy a book, okay, and then robot will have milk, bread and book. Now, is it okay? Is it the final plan?
No.
Okay, so what is left over?
Return.
What is
Go home.
right? Correct. So after performing this, robot will be at bookstore only. Okay, we want robot should be at home. This should be true. So we will add a step go home here from bookstore. So robot will be at bookstore. So we have added a step addition is performed go home. So robot will be at home. So at home will be true in that particular case. Okay. Now this is the final plan. And uh, again one more demotion you will be doing after buying a book. Robot will be at bookstore. So demote go home from buy book to go home. One more demotion you have added. So three demotions you have added into the plan. So three is removed by three demotions. Okay. Because the precondition was not satisfied. So to satisfy that precondition, demotion step addition is done and threat is removed. Very interesting. So this has generated a plan. Now this tells you how robot should work, right? So there are different partial plans that has generated and that has resulted in a final solution. So first S1 will be performed, robot will go store, then it will buy bread and milk, then go to the bookstore, then buy a book, and then will go home. Okay, so and then robot will have milk, bread, book, and robot will be at home. So actions that has to be performed are go to the store, first action, then buy milk and buy bread, then go to the bookstore, buy book, then go home, and finally finish. So start, go store, buy milk, buy bread, go bookstore, go home and buy book. So this is the set of actions. Or start, go store, buy bread, then buy milk, then go to the bookstore, buy book, then go home and finally finish. So all sub goals will be satisfied. So threats are removed. So final partial order plan will look like this. This is the final partial order plan. Same thing, only now all links, causal links are black color and demotions they have been shown with blue color arcs. So in this way, problem solving will be done and generally such a programs are written. Uh, for example, navigation robots or rover kind of robots. To operate them, you will have to prepare such a plans and then you will have to perform coding. And to search through this, some search technique you will have to use, as I told, like iterative deepening, DFS, or breadth first search kind of techniques can be used to search through these partial order plans. Any question up to this?
No, sir.
This is not given in your Rich and Nights book. Some other example is given. But this is a very good example. Discuss at many of the uh, online lectures you will find out. So let us summarize. This partial order plan algorithm is sound and complete. That means it returns a solution. That means a complete plan. Then any total ordering implied by it solve the planning problem. So therefore it is sound. And if there is a solution to a planning problem, partial order plan algorithm will eventually solve it. So therefore it is complete. So therefore we say that it is sound and complete. Whenever you are going to write a program, so usual implementation of this maintains a queue of partial plans and sort these queues using some kind of ranking function. And accordingly, the effective efficient plan is generated. Okay. So it's an interesting, actually, now you might have realized that whatever we have discussed in course of AI, how it is used, all those concepts, they are used in reality, in real world. Specifically, the problems like robot navigation or how robots are programmed. So robots are programmed with such a techniques. So knowledge is represented in the form of logic, first order predicate logic, that kind of form, and appropriate problem solving techniques are used for achieving goal. One of the technique that we have discussed today, that was partial order plan. So we will stop here today, and in the next lecture, that most probably will be our last lecture on this course, we will discuss graph plan algorithm and non-linear planning. Okay. Any question?
No, sir.
Okay, so we'll stop here. Thank you. Good day.
सर एक्स्टर्नल एक्झामिनेशनचं काही. हॅलो.